So what's LXD? Well, LXD is what we call a container iterizer. That's basically our intent with that naming is that it gives you the same kind of feature as you would for a virtual machine, and you would expect from a virtual machine hypervisor, but it doesn't give you all the downsides of it. So you don't get performance impact. You don't, like an idle workload, it's not going to kill you with interrupts, all of that kind of stuff. It's really designed to be simple. It is tiny daemon offers a REST API. The REST API itself is pretty easy to interact with if you want to do so directly. It is meant to be extremely fast. No resolution overhead. There is a negligible overhead of the C groups. If you do some crazy resource limitation, you might actually see tiny overhead. But besides that, it's basically as you would expect from a physical machine. It is secure by default. That is pretty important compared to some of the other projects. They're actually catching up now. But we do use an interfaces by default. We do seccomp, we support SE Linux, we do AppArmor, C groups, capabilities. I think that's what then. So we basically use every single kernel security feature that exists, and we combine all of those to make an extremely safe container out of that. I'll actually show you towards the end. We have a live demo on our website. You can actually go on our website, click something, and you get access as root inside of an LXD container that itself can run nested LXD containers. So we basically have trusted around 11,000 people with root access right now, and haven't had a single problem with it. It is scalable. The design is really that both the tooling and the API and all of that works perfectly well on your laptop to run a few containers just for fun. Will run just fine in like a small business environment where you might have like production staging, whatever servers, and plus the developer laptops, or then full scale enterprise or HPC kind of scale where you have possibly thousands of nodes. We basically support all of that. The design is that the LXD daemon itself always cares about what's running on a given host. It doesn't care about what's on the others. So you can actually scale as far as you want, so long as whatever you're using for scheduling in front of that is sane. So that's what the architecture kind of looks like. You've got a bunch of physical hosts. You've got the Linux kernel on that. We run LXC. Which is like the LXD library, and then LXD is sitting on top of that. It offers a REST API, and then we've got a bunch of clients. The demo I'll show you later is using our command line client, but we also have an OpenStack component. So you can deploy OpenStack with the Nova LXD driver, and then people can deploy containers just as they would VMs. From the UI and from the API, it's absolutely identical, except it deploys using LXD. And it's pretty easy to script. In fact, if you go look on my blog, I posted something yesterday, the day before, that shows you how to drive LXD just using curl. And showing you how to create containers, snapshots, reading files, pushing files, all that stuff, just using curl from the command line. Now, what LXD isn't, it is not a new virtualization technology, because while we're doing containers, we don't have any overhead, we don't need any kind of virtualization extension whatsoever. We, in fact, run LXD on every architecture that Ubuntu supports, so that's AMD 64, x86, PowerPC, PowerPC64EL, ARM, HF, ARM 64, and even S390X, so IBM System Z. And it works identically everywhere. It is not a fork of LXC because it is using the LXC library. We no longer use the old LXC tools when you use LXD. Those tools were pretty complicated and people were kind of getting lost. So LXD was a great way of us to rethink that experience and come up with something way more user-friendly. But we still use the LXC API. LXD itself doesn't know how to create containers, it just talks to the LXC API and LXC does it for it. Which means that any feature we add to LXD, we first add to libLXC, which means that if you want to build your own thing on top of libLXC and bypass LXD, you're welcome to do so, and it works great. And it's not an application container manager. So, clarify that point. LXD really focuses on running a full system as you would in a virtual machine, so that it doesn't care at all about what's running in your container. It's execs has been init, and that's it. After that, it's up to your container runtime to do its thing. We don't do any kind of redirection of any of that stuff because, again, we don't know what's running in a container, and frankly, we don't care. On a network side, what we do is basically, hey, give us a bridge, and we give you layer 2 to the container, and then we can do the HTTP or whatever the hell you want inside it, and that's fine. So we're not like competing with Docker or Rocket or any of those guys because, yeah, we're not distributing apps, we're distributing Linux distributions. However, we did work quite a bit this year, and we've had it working for like a month now in Ubuntu. You can run Docker inside the LXD container. That actually works. So you can create an unprivileged LXD container with all the security features enabled, and then run your untrusted Docker container inside it. That works fine. That has an extra security layer. Also means you can partition physical hosts for a bunch of users. Then those users are welcome to either run a nested LXD daemon inside it for their own LXD containers, or they're welcome to just run Docker if they rather. Briefly, like enterprise scale kind of thing for LXD. As I mentioned, it does integrate with the OpenStack as we ship it in Ubuntu. It's the Nova LXD project that does that. Nova LXD itself is based on PyLXD binding for API. So if you want to drive LXD using Python scripts, you can use the same binding we're using for Nova LXD directly and use that. When you use it through OpenStack, as I said, it's completely transparent. You don't even really know that you're running LXD. If you really look deep in the UI, you'll see somewhere that the runtime is LXD and it's not KVM. But that's basically the only difference you'll notice. It is perfect for idle workloads because we don't waste any time scheduling, having to deal with interrupts and whatnot inside the VM. And it's all running on the same Linux kernel, so if you're not doing anything, the kernel doesn't give you any time, and we're done. That means that, like on my crappy Xeon Alone that I'm using for scale testing, it's like a 6 years old dual quad core Xeon thing. It's really crappy. I'm running about 8,000 containers on it, and it's perfectly fine because those containers don't do anything. So it does take a while to start them because then the load spikes quite a bit, but wait an hour after that and the load goes down to basically 0. Which is exactly what you would expect to see. I don't expect to be able to run more than maybe 20 virtual machines on that machine before it just dies. Negligible overhead, that's basically what I just mentioned. And then we've got fine-grained resource limits, which you may not always get with virtual machines. More importantly, all of our resource limitation code in LXD can be changed live at any point in time. You can shrink or grow your resource limits, and they just apply immediately. It's not always that easy with a virtual machine. And the other thing is that you get much nicer introspection into what's actually running if your host is getting extremely loaded. If it's KVM, what you'll see is that KVM is using 100% CPU. That's not really telling you much. With LXD, obviously, you can do a PS and you see the actual task, and if it's got nothing to do there, you can just kill it. Another thing we've been working very actively, and I'm really happy that this, as of yesterday evening, it actually works, because I can actually demo that afterwards. We do have integration with Creo. So Creo is the checkpoint restore in user space project. It was started by the guys at Parallels in Russia for OpenVZ originally, but LXC has actually, weirdly enough, been the first container runtime to support it before OpenVZ. And we've been working pretty closely with those guys to make sure that you can take a safe default LXD container and you can checkpoint its state and restore it. So the features we do support, the most obvious one is container live migration. You can move a container from one host to the other, but everything still works. The process just looks like it's paused for a couple of seconds or whatever it takes to actually move the process state across. We'll actually be working quite a bit more over the next 6 months to improve that thing. Right now we pause the process, then transfer the whole memory in one chunk. That's kind of bad if you've got 40 gigs or whatever of memory being used, because it's going to take a while to transfer. There is support for incremental memory page transfer that's being added to Creo right now, so we hope to get to use that very soon, because then we can minimize the downtime to hopefully just a few milliseconds, by doing incremental memory push until the delta is small enough that we can just push the rest after we've done the processes. The other thing we support with the exact same tool is stateful snapshots. So you can usually do your, LXD supports normal snapshots. You run a container, you snapshot it. If you revert it, your file system is reverted to the original point. That's snapshot 101. But you can also pass a stateful flag. And if you do so, then the container state is also recorded in the snapshot. I'll have that in my demo, but yeah, basically if you run really complex services that really complex state and that take forever to restart, and you're going to do something bad, I don't know, do a big upgrade or whatever that might affect it somehow, you can checkpoint that thing, and if it fails, you can restore it, and process will actually go back in time and continue from wherever it was. You can even use that as the way of doing like backup of your state, so you could automatically snapshot every hour or something, and if your machine crashes for whatever reason, you restart it, you restore from the last snapshot, and your process starts exactly where it was an hour ago. And similarly, we support stateful container stop and start, so that means that, say, I want to do a kernel upgrade because of a crazy security issue or something, I can stop all of my containers, passing the flag saying, hey, I want that stop to be stateful, and the state will be recorded, the container will stop. You can reboot your machine, and when you start them again, the state is restored, and things start exactly where they were. And obviously that gets tricky if you've got processes that talk across the network, because you kind of need to do all of them exactly at once, otherwise they're going to get out of sync. But at least on a local machine, it is pretty convenient. And yeah, this lets you do pretty interesting things. One case actually I forgot to mention, because we've not widely tested it, is we do support stateful images. Well, we hope to support, let's say. So you could, in theory, and I guess it's mostly useful for some database guys that have like massive databases where it takes days to get a warm cache. They could, in theory, on their staging system, pre-warm the cache, publish that as an image, and then deploy it to a bunch of production database servers. And when those containers start, the database server has already been run for a day, and its cache is warm, which could be interesting. And so that was for the boring part of my presentation. Now I can actually do the cool stuff. So demo. I need this one over there. That's right. And I'm gonna need this one here. That looks right too. And I'm gonna need this. There we go. Okay. So most basic thing ever. Just starting a new LXD container. Oh, yeah, latency of 5 seconds to the internet is not good.
Internet connectivity is a lot.
Yeah, it doesn't need to pull much. It needs to pull a few Ks to make it happen. Hopefully it will very soon.
Maybe what we could do, to accelerate this demo, it's just close your laptops, not two. I'm not kidding. Because well, it's what we have. It's university.
You need to ask Wiki. I can share with her my Wiki. Maybe if we wait like this.
Woohoo! Okay. So it eventually did manage to get the few Ks it needed from the internet. Just took. It usually takes maybe half a second to do that. But yeah, Wi-Fi is kind of crappy here. So that's created a new container for you. Yes, sorry for that. I think 6 addresses take quite a bit of horizontal space, so it doesn't look as pretty as it would on your laptop. We see the test container is running. You can get a shell inside it. You can look at whatever's running inside that container. You're gonna probably see the and Wi-Fi is kind of working now. Well, with 50% packet loss, but anyway, so that's basically starting a container, getting a shell inside it, all is great. Now, I've got some existing containers, and that one was just to show you how to create one. I don't really need it anymore, so we can get rid of it. And that's it, it's gone. I do have an existing container called downloader. I've got one called streamer. Oh, yeah, thank you. So I do have an existing container called downloader, one called streamer. Streamer basically runs two tiny services right now. One is the smallest Python HTTP server you can possibly do, which serves a 100 gig empty file. The other one is a tiny UDP service which just pushes an incremental number over UDP. First, we can play with the HTTP side of it. So if I go in the downloader and download from the streamer, we'll see I'm getting reasonably good speed between those two containers, about 8 gigabit a second or so. So not too bad. Now, if I want to apply some resource limits, one thing I can do is, and that might get cropped a bit or not, let's set the ETH0 device speed to 100 megabit. And if we go back to the download, we see it's now shrinking, getting down to 100 megabit. Or I could bump it to, I don't know, 320 or some weird number, and we'll see it get back up. So that's basic network limitation. If we want to remove the limit, we can unset it, and we'll see it go back to its 10 gigabit-ish speed. Now, the other thing I can do, if I look at POC CPU info in there, we'll see that I currently see all my laptop CPUs, so that's 4 of them right now, 2 cores with 2 threads each. I can limit that too. The most basic one is just the LXD. You want, say, 2 CPUs. And now if you go and look at it again, it would work better if I was actually showing personality. There we go, I just have 2. What LXD does, it's using the C group, CPUs at C group, but because CPUs at C group doesn't let you say, I just want 2 CPUs, you have to do specific pinning. LXD has a background process which monitors view events and will automatically load balance your containers. If you add more CPUs, it will spread them across the new CPUs. If you remove CPUs, they want to be moved away from them. Yes?
Can you also limit GPUs?
Not right now. We've been talking with NVIDIA a bit. CUDA is kind of weird. We do have some hope that yes, you should be able to do so.
Or just if I have like 4 GPUs in the system that you know, this container only gets access to.
So yeah, one thing I'll show tiny bit later is you can pass any character device you want inside the container. So if they show up as 4 different character devices on the host, it's trivial to just pass the one you want inside the container. And we could, and I think it's planned to add a layer of abstraction, so we can actually say, hey, give me GPUs, and you don't have to actually care about the actual child device, and just does it for you. So that's basic CPU if you just say, hey, I want 2 CPUs. Now, obviously, in some cases, you'll actually want to set exactly what you want. So say you want CPU 0 and CPU 223. You can set that, and you're good. And with that kind of expression, obviously, it's going to be a static pinning. So if you remove one of those CPUs from the system, it disappears. If it comes back, it shows up again. It will not load balance you in that case. We can set that limit now. And another thing that might be useful too for some people is we support some of our syntaxes. So with the allowance syntax, you can say, I want 20 milliseconds out of every 50. And that's going to be enforced by the Linux scheduler, so you'll never be able to exceed that. And it's not guaranteed, because unless you're running a real-time kernel or something, we cannot really guarantee that. But we can guarantee you're not going to be able to exceed that. So that's another useful syntax we've got in there. And set that thing too. Now, we can see here that I've got 12 gigs of RAM currently visible in the container, which is the total amount I've got on my host. Again, we can limit that with limits.memory and say 1 gig. And if I go back in the container, we're down to 1 gig. Or you can say I want 20% of whatever the host has, and I'll get 20% of whatever the host has. I'm not going to go in more details for the memory stuff, but well, in a demo, but we can also turn swap on and off per container. We can give a swap priority to the container, so containers you don't really care about are going to be swapped out first. We have quite a few options around that. Memory limit is implemented in hard mode, so compared to CPU, if you just set like a CPU priority, it's only going to apply on a load. For memory, it's by default, when you reach that total amount of memory, the out of memory killer starts having fun and kills your processes. You can set it to soft mode if you want to, which gets a bit awkward because you can actually exceed your memory allocation, but as soon as something else tries to get memory that they actually need to get, then the out of memory killer starts killing your stuff. Which it makes sense, but it's kind of awkward because we're like, but I managed to allocate that memory, why the hell is it triggering now? So that's why we don't do it by default. And then the other obvious limit is you can set the, again I should show what I've got right now. Right now, slash for that container, it's stored on ZFS, and I've got 148 gigs. I can change that by setting root size to, let's see, 10 gig. Oops, works better if I have the right thing. And it's wrong. There we go. If I fix all the typos, it actually works. And we see we're down to 10 gigs-ish because our disks are weird. And we can set that limit to get back to whatever I had. So that's basically resource limits for you. There are some more things that are a bit difficult to demo. We do have various priority options, so you can say that if under load, what container will get to the network first, if under load, what container will get to your block device first. We also support limits on block devices by in byte per second or in IOPS. But because I'm using ZFS, and ZFS is kind of weird in a sense, in the way it's plugged into the Linux kernel, those limits only apply to some operations, and because I'm using a ZFS in RAID mode, it gets really, really confusing. So if you're using straight X4, IO limits work great. If you're using anything else, they are a bit awkward, mostly because of the design in the kernel for those. So that was just setting basically all the limits that we have. Now, other things we support, we can pass devices into the container. And as you notice, all of those limits apply immediately. The container is not restarted. All of that stuff is completely live, which is kind of convenient. Oh, maybe one thing I can show you too. If I was to edit, so LXD has profiles. Profiles are basically a group of configuration keys. And if I edit the default profile, which all my containers have applied to them right now, I could say on the default network card, well actually let's just do a CPU limit instead anyway. So I can go limits.cpu and set it to 2. There we go, and now if I go in the loader container, I've got 2 CPUs, and if I go in, the other one is streamer, so I can go in streamer. I also have 2. So you can actually change all your containers in one shot by just having them all share a single profile, and that's all you need. So let's remove that, and that limit's been removed. Now, other things we can do live is adding devices. So this command is kind of long, but what it does is it takes my physical ETH0 device on my laptop and passes it into the loader container as ETH1. So I run that, I go into the loader. Oops, that's no longer the loader, that's the loader. And there we go. And I can, actually if I check on the host, it no longer exists because it just got passed into the container. And I removed it from the container and it's back on the host. So that can be pretty useful in some cases. The other thing you can do, and that's what I've just mentioned for the NVIDIA thing, you can pass Unix child devices or Unix plug devices into the container. So in this case, I'm going to pass KVM, so dev KVM into the container, which would then allow you to run QEMU virtual machines inside the container if you wanted to. That's actually how I usually run them because I don't really trust the QEMU binary. So if I do that, then I go into the loader and we'll see that I've got dev KVM in there. Again, same thing if I remove it. And I go check again, it's gone. And those you can also add to a profile, and everything that is in that profile will automatically get those immediately. Now, something else you can do with containers with LXD is easily read the container file system and files in general. So if you want to get the syslog from a given container, you can use the file pull command to get varlog syslog and spit it out to start in this case and migrate into less, and there we go. The interesting thing there compared to other management tools is because you're accessing the container using LXD, if the container doesn't have any networking right now because your network config is fucked up somehow, you can still perfectly read any configuration file, read any log file, you can edit those, you can push a fixed one, whatever you want. You can get a shell inside your container despite it not having network access. That all works perfectly fine. Now say we can pull a file, in this case a post file. Let's just add a bogus entry to that. And then we can push it back to the container, and we can check that it's actually right because there's even an edit command. So you can just do edit and then file, and we see that it's right. Now, the most basic snapshotting you can do for containers, just snapshot its state. So I'll just snapshot downloader actually. So there we go, it's snapshotted. If we go look at downloader, we see it's got one snapshot all over the bottom. It's called S1, it was taken right now, and it's stateless. The other thing we can see in that LXD info comment I just forgot to mention earlier is the existing resource consumption. So we can see how many processes are running in a container, how much space is currently being used for on the file system. As you can see, that's a full Ubuntu container, but because it's using ZFS and doing cloning, it actually only uses 9 megs. Kind of convenient. We can see how much memory it's using right now, which is about 18 megs, and how much memory it's used at its peak, so that was about 74, probably somewhere around the time. And then you've got interface information for how much data you actually pulled to it. So that was basic snapshot. Another thing that I mentioned earlier, you can actually nest LXD, so let's try to do that. I'm going to start a new container called nesting. It's going to use the Ubuntu 16.04 image, the latest one available. And we set here that config option, because you can actually pass config options at launch time too if you want to. That nesting will be enabled. Again, depending on Wi-Fi, that might take a few seconds. It's only downloading image index, but that's been known to be kind of slow. Oh, there we go, simply done. So we've got that container running right now. If I go into it, I can do, say, list, just generating a certificate to that LXD, and it shows nothing. But then we could start containers, which I won't do because then it would need to download stuff from the internet, and that's gonna be a problem.
One question.
Yes.
You're using all-time LXC, okay?
Mm-hmm.
And now what it says there that this is your first time using LXD. I mean.
Oh yeah. And unfortunately the naming wasn't really up to me, but so the client for LXD is LXC, but the init command in that case is a server-only init command that sets up storage and networking and all that kind of stuff, which you must run on the server itself.
So you're using LXD here.
Yeah, all the commands I showed so far are actually talking to LXD. The difference, basically, if you've got LXC-something, that's the old LXC command. If it's just LXC space something, that's going to be the LXD command. Yes, it's confusing. If you say directory, it's just, by default, on X4, it's basically just going to deal with tarballs and then packing those. That's kind of slow. Also, if you make a snapshot, it means it's going to rsync the root file system. It works, but it's really slow. Unless your valid LXD directory is on VeloFS, in which case it's gonna do subvolumes and stuff automatically for you. So as far as storage, we basically support plain old directories, VeloFS, ZFS, and LVM. And when you do LVM, it's spin provisioning with X4 or XFS. We recommend ZFS because of stability, and it's got the features we kind of need. VeloFS has similar features, slightly less stable, but might be better for some people who want to install ZFS. So in this case, it detected that I'm running nested, so it suggests that it could do a tiny setting to make my life a bit easier. So I'm going to say yes or not. And then it's asking me whether I want to configure the network, so sure, why not? In which case, whether I want to have it visible over the network, so sure, let's bind to, let's make it binding to anything, and use the default port, and some password, and password again. And then it asks me whether I want to configure the LXD bridge itself, which is how all the containers get networking. For those using LXC before, you might have noticed the LXC BR0. It came pre-configured with a subnet, which was a bit unfortunate because that subnet is sometimes used by people, and that kind of masks your network, and that's not so good. So LXD comes with a bridge with no subnet whatsoever. The only thing that's configured by default is a link local IPv6, which cannot possibly configure with anything. And we run a tiny HTTP proxy on it so that you can at least install packages, but that's about all that's going to work. You do need to run through the bridge configuration, which asks you whether you want to configure it. Yes. Choose the name of the bridge. Sure, why not? Then if you want IPv4, you can say yes. It's going to try and be clever, so it's going to get a random subnet, then check whether it pings on .1 or .254, and then tell you that, hey, it's a random subnet. You still want to look at it, but it pre-fills it. So in most cases, you can just hit enter. Then it does configures NAT, and then it does the same thing for IPv6. Again, it's trying to figure out a random subnet. It uses the site local range for IPv6 addresses, pre-fills everything, and because it's a site local, you can need to NAT it, so it doesn't do, and you're done. So it's pretty easy to set IPv4 and IPv6 the right way, and obviously you can use any kind of setting you want. I did get an email yesterday from someone doing scale testing with LXD, ran through that, but kind of forgot that if they want to run more than 250 containers, it's useful to have a subnet that's bigger than /24. So if you want to run more than 250 containers, use a /16 or something. And that's pretty much it for nesting. One thing I can show you is, I mentioned that we can use Docker. I'm looking to install it because that's going to take ages, but the configuration you need to do to have it working is, we've got an extra profile for Docker, which is called Docker, so you need to apply the right stuff profile. So apply the default profile, which gets you networking, and the Docker profile on top. So you just do that, and now I could apt-get install docker.io in there and run it, and that will work. Except, yeah, not here. Okay, that's pretty much it for basic interaction. I'm just trying to figure out whether I forgot anything major. I didn't really, but one thing I could show you maybe is you can see the container configuration with config show. Let's say get the downloader, and we see all the configuration keys are applied. We see it's still got a limit of 20% of the memory. It's got some data as to what image it was built from. That's pretty useful for us because when you try to move a container from one host to another, it will check whether the image exists on the target host. If it does, it's going to pre-create a target container with that image and then only transfer the delta across. So that saves you quite a bit of bandwidth. And then it stores the current MAC address and the username space UID mapping so that it knows what's currently applied to the container. We see the devices that are directly applied to the container, so we've got ETH0 in that case. If I look at the streamer container instead, it doesn't have that device because it's coming from a profile. If you want to see the total config, including all the profiles, you can do --expanded, and that shows you the actual runtime config instead of what's local in the container. We have a bunch of edit comments that are kind of useful because they just bring you into an editor with an example config and shows you your stuff. So you can do xcconfig streamer in this case, and it opens my default editor, shows me all the config. I can do any change I want. When you save, they are live applied to the container. What's anything else I should show you for that part of the demo? Don't think so. So we can go to the actual exciting stuff. So I mentioned Creo earlier, and also mentioned that I actually got it working. So the other thing I'm running inside that streamer container is a tiny UDP service, you call it. All it does is it sends a number to an IP address every second. We see it's currently at 7,000 something. Now, before I did a snapshot that was stateless, but let's try to make a snapshot that's stateful. So want to, well, let's just call it S1 and make that a stateful snapshot. So it's going to snapshot the streamer container, creating an S1 snapshot. There we go, it's done. If I look at streamer, we see it's got a snapshot taken right now, and it's got state inside it. So now if we go look at the UDP thing, it's currently at 7,000 and basically 60. If I restore streamer S1, so I'm restoring the container, and I go check, it just went back to 7,050 now. So it basically restored all the memory state and everything, including that UDP service I was running, so it went back in time and kept on going. So that's nice. Now, the other thing I can do is stopping the container. So let's do stop of streamer, but instead of a normal stop, which would actually shut everything down, we're going to do the stateful sharp stop. So let's do off. Okay, but you see it's no longer doing anything. In fact, if we go and look at runtime watch things running, no more processes running from that container at all. And okay, fine, we can start it again. And we see the two processes are running again, and we see just restarted where it was. The other thing I could show is like we have something, so that's basically equivalent to say a suspend to disk kind of use case. We have an equivalent of suspend to RAM, I guess, which is pause if you do not. It also stops counting, except that the tasks are still running, but they're basically no longer getting scheduled, so you still use the memory on the host, you no longer use any of the CPU. It is obviously way easier to do that than doing the whole dumping state to disk. So depending on your use case, that might be interesting too. Then you do start, and it's going to start again. There we go. So that's basically your stop, start, stateful. That can be that's what you would do if you were to do like a kernel upgrade or something. You can dump every container state to disk, then you reboot your machine, and you restore it. One thing you want on that, I mean, Creo is pretty new. Not everything works very far from it. When it fails, it usually fails nicely. So it fails at checkpoint time rather than at restore time in most cases. So it doesn't actually kill your container, it just keeps running and tells you it couldn't actually store anything. And it gives you a really detailed log that you can then send us, and we'll have one of our kernel guys look at it and implement whatever is missing. Because a lot is missing. It is really difficult for a user-space process to dump every single kernel structure to disk and then restore them. It's working for a default use case, it's not working for a lot of things, and we absolutely want to fix that. That's going to take years to get support for everything. The other thing, what was I going to say? There was another limitation of Creo, or maybe not.
So you rely on shared file system?
We don't
enable migration?
Actually, we don't. So for that migration, what we do is LXD itself in storage backend does know the different file systems. If you use something like X4 or anything that doesn't do that migration itself, it's gonna do an async for you essentially, which is kind of slow, but it does in 2 steps, so it's okay. If you use BRFS or ZFS, it's going to do the same receive for you. So it's going to send your snapshots incrementally, and then it's going to send a state as the last thing. Creo does require a really recent kernel, and we have like the Ubuntu 4.4 custom patched kernel does work. Creo also doesn't work on all architectures. As far as I'm aware, it does on AMD64, so x86 64-bit, and I think they have v7, and I believe IBM kind of finished the support for Power 8. But yeah, it's getting there slowly. It is pretty tricky because we need a bunch of new C calls and things in the kernel to actually make that thing work. But yeah, it does spit out pretty good logs that you can send us, and we'll definitely look into that. LXD doesn't actually depend on Creo by default. It is voluntarily an opt-in thing that you need to install Creo separately and then start working. Now the other use case that I guess some of you were waiting for is actual live migration. So I'm just going to show you what happens when you, because I actually didn't go through that. The LXD command line tool can talk to any number of machines. Right now I've only been dealing with my local machine, but if I do a remote list, you'll see that I've got a fair few because I'm managing a bunch of different machines for different reasons. So I've got a few of them. You can interact with them by prefixing any container or action with the remote name and a column. So say you want to list, I've got a remote locally here for live migration, it's called LXD1. So I can do LXD list LXD1 column, and that shows me what's running on there. Now if I want to get, say, a shell inside that streamer1 container, I can just do this, and I'm in there. That's using the LXD REST API to talk to it. So that's pretty nice. Now, well, let's see if that actually works. That kind of depends on the internet, so we'll see. We ship with four different default remotes actually. You've got local, which is the default remote, so you don't actually need to set its name. I should start by that to left, sorry. That's one, yeah, it's the default, you don't have to type its name. You can actually change that default to something else. If you don't run LXD local, you just run it on some other server, you can set that as the default, and it works the same way. And we ship remotes called images, which are unofficial images that exist on the LXD image server. And then we ship an Ubuntu and an Ubuntu daily remote. Both of those are official Ubuntu images. The Ubuntu ones are the tested ones, dailies are dailies. So, here I'm listing all the images that exist on the community run server. So we've got Alpine Linux, we've got CentOS, Debian, what else? Fedora, OpenSUSE, Gentoo, Oracle, Enterprise Linux, Plamo for if there's any Japanese people in the room. Then other tinier Ubuntu images, because the one that Canonical publishes officially are the full cloud images, which are kind of big, they're like 300 megs or so. We publish tinier ones on that unofficial server. And then we publish older images too, if you have, for some reason you want to get an image from like a few days ago. So back to that actual demo. So we've got that container called streamer1. Streamer1 does the same thing as streamer, which is it prints numbers. And it's that console here. We can actually prove that by pausing it. So if I do LXD1, streamer1, it's paused, it should start printing numbers. And it does. Okay, fine, get started again. There we go. And now we can move it. So I'm just going to move it to my local machine. We'll say it keeps going for a while because it's actually transferring the file system in the background, and there's no reason to actually stop any task while that's going on. And depending on how my virtual machine is feeling, it might take quite a while. I've had some local networking issues that I've not actually figured out yet. Come on. Eventually we'll see it kind of freeze, probably I think for about 2 or 3 seconds, and then it restarts on, and should work fine. Come on. Oh, it's freezing. And it's starting again. And now if we go check, on my local one I've got streamer1 running, on the LXD one I've got nothing running. So it just moved and it kept doing what it was doing. I remember what I wanted to say before with Creo. So other limitations that are kind of obvious but probably worth stating. If you are migrating from a new kernel to an old kernel and syscalls disappear in between, your workload is going to be really unhappy. As in, it's going to try and call the syscall that it already pre-checked for earlier, and it's going to say fault. Same thing if you try and move from a very fancy new CPU to an old CPU, and that program was doing runtime optimization at start time. It's going to try and call extensions and stuff that don't exist, and that's going to blow up. So usually you want to move between, you only want to move forward as far as the kernel, and you only want to move between machines that are the same generation as far as CPU extensions. But besides that, it usually works. It actually did. So that's pretty much it for the demo. Can go back to slides. There. Righty. So, just a quick recap on what LXD is. So it is a simple but very powerful REST API to manage infrastructure containers. Infrastructure containers is another name for system containers. So full Linux distribution kind of thing. Again, we don't really care about what's running in the container. If you want to render code inside it, that's perfectly fine. It is entirely image-based. That's in contrast to what old LXD was doing, where you had those template scripts that would basically build yourself a root file system. LXD is entirely using images. It's pretty easy to build an image. An LXD image is basically a compressed root file system and a tiny bit of YAML that sets what architecture it is, when it was built, some properties, that kind of stuff. Really easy to do. You can even do it as two different tables. You can have one that's just your root file system, which you might use for other tools, and then the next to the table with just the LXD bits. Our containers are, as far as I know as of today, because kernel bugs show up every day, but are safe. You usually want to look pretty closely at security announcements for anything kernel related and apply those as quickly as you possibly can, because any kind of root escalation exploit obviously will also impact us, and you might be able to escape the container, which would be kind of bad. It is very much scalable because of different designers. We don't try to have LXD, the daemon itself, be aware of multiple hosts. We really don't. But you can then have different management tools on top that then manage a lot of different hosts. On that regard, I meant to just mention security for that aspect. When you move from one host to another, the target host doesn't get any kind of credentials or anything that lets it do whatever it wants on the source host. What happens is that the client tells the first host that it's going to get migrated. That generates a one-time token. That one-time token is sent as part of the migration request on the target host, and then alongside this source server certificate, then the target will connect to the source using that token, which only lets it read the one container it needs to move. And since it's got the certificate for that server, it will also check that it actually matches, so no man in the middle whatsoever. We're trying to take security very seriously. We're also TLS 1.2 only and elliptic curve ciphers only. Basically anything that's vaguely legacy is gone. We just don't care. And it's designed with both developers and enterprise in mind. As shown, like, it's really, really easy to use on your local machine. It's just as easy to use. That command line tool, I've used it with up to 8,000 containers, and it basically works the same way. The only problem is that list gets really slow because it needs to go and look into every container for the network information. That's unfortunately pretty slow in the kernel. So we have a -- fast option, which basically hides anything that's slow to get and just gets you the rest. So you can use that. Or you can even pass filters. You can just pass like a partial container name, and it's only going to actually query those. A bit more technical details on LXD itself. It is written in Go. It can be translated, as far as I'm aware, in LXD 2.0, which we released 2 weeks ago. It will be the one in 6.04. It's only translated into Japanese right now. But you could submit .po, and we'll be very happy to merge that. We've got because our code is in Go, the command line tool is in Go, so we've got an API client in Go. But we also have that Python binding I mentioned that we're using for the OpenStack bits. LXD itself is Apache 2 license, and we do not require a signature of a CLA or any of that stuff. If you want to contribute, all you have to do is to be signed off by DCO, standard thing for contributing to projects related to the Linux kernel. That's it. And that's it. I just wanted to show you that website. Let's see if that actually loads. Then take a few questions if there are any. Let's see. Okay. Oops, didn't go on the right screen. This one. There we go. Okay, so it did load. That's nice. We can see there are currently 9 users using our demo service. That's the URL I printed at the bottom of the slide. I'll show it in a bit again. what you can do is you've got the basic time of service. It tells you that our demo server will get you access for 30 minutes. You can actually reconnect if you want. You can even do so with up to 5 sessions in parallel, so you can try moving containers between those sessions. We don't do live migration, and we don't do Docker in that environment because it's, well, we just can't migrate nested containers, which those are. And enabling Docker would have meant enabling access to all of the Amazon subnet from those containers, which wasn't really an option. So no Docker, unfortunately. Then we've got, you get one CPU core, 256 megs of dedicated memory, 5 gig of disk space, and basically no network connectivity. You only get IPv6, and you only get IPv6 to the few subnets we actually care about. I think it's blocked. Anyway, you click on that thing. It usually takes about 3 seconds to get one, but because internet might take a bit longer. There we go. So you get that container running. It's still initializing. It should actually shrink down to a little bit less processes and a tiny bit. Anyway, you can start a new container. So it's blah, which it's doing right now. The server we're running that stuff on doesn't have a lot of entropy, so it's kind of slow to generate the initial key. There we go. Then it's downloading the image at a much nicer speed than we do here. Then it's unpacking that thing into a BRFS volume. So the first time you actually do this, it's kind of slow because it needs to create a BRFS volume for you, unpack everything inside it, etc. It's pretty slow the first time. I'll do it the second time afterwards. It's going to be much faster. There we go. Container is created. Now if I want to create blah1, let's do the same thing. And we're done. So yeah, it's significantly faster the second time once the volume has actually been created first. And we see both of them are running. And you actually have a nice step-by-step demo thing below. That's usually the demo I would give in most conferences. You can actually click through it. If you want, it says here that you need to create your first container, so you can click on the command init execs up there. Then say, oh, you want resource limits, so you can click free, you can click free in that one, and you'll see that they're running there. And then you can do config set, that's running. There we go. Then we can check again the memory, and we see the memory limit has been set. So it is pretty convenient for people to click through and have fun. I think we are up to about 11,000 users who've played with that thing so far, so it's a nice way of showing LXD and for us to stress test our security story. I've also been working on a blog post series on LXD 2.0 on my website, basically explaining how everything works, going into details in all the commands and stuff. I think I'm up at blog post 8 or something on that series, 4 more to come. The next one is on live migration. It was on hold because of the kernel issue. I'm probably going to be working on a blog post later today. And that's it. Any questions?